A couple of announcements before we begin today. Let's see. I apologize about the lack of office hours this week. This has been a crazy week. Hopefully you got my email this morning. I'm going to have extra office hours next week to make up for the missed office hours this week. If the hours that I sent out this morning don't work for you, send me an email. I actually have pretty good availability next week, so we can set up an appointment to meet at a time that's convenient for you if you want to come in and talk to me about the next homework assignment. And just as a reminder, that assignment is due 1 week from today. So hopefully you've already gotten started on that. We may have some time towards the end of class today to talk about that particular assignment a little bit. Are there any questions about the assignment that I can answer for you right now, actually, while we're on the topic? Okay. I feel like there was something else that I needed to discuss as well, and I cannot remember it right now. So it must not have been that important, I guess. If it comes back to me, I'll let you know. Okay. So today our topic is going to be operating systems. So I've got 2 papers that I want to talk to you about today. I've linked both papers on the course website. I think these are actually very interesting papers. So, I mean, if you want to just sit down and read them, I think that would be a great thing to do. But I'll kind of go over them in class today and give you sort of a high-level look at both of these papers. The first one is a little bit on the older side. I think it's from about 10 years ago. And then the second one is a bit more recent. And they both describe 2 different kinds of operating systems for high-performance use. Before we get to the papers, just kind of a brief introduction to the concept of operating systems in the field of high-performance computing. In the past, the first supercomputers had very few cores involved. There was just a single core, which means that the operating systems were really just glorified job schedulers. The first kind of operating system-like thing on the first supercomputer, which was a CDC supercomputer back in the 70s, I believe, was a job scheduler called Chippewa. It didn't even really have an operating system. You just plugged in a job and it cranked out the results. The first real operating system, more operating system like than just a job scheduler, was developed by Cray back in the late 70s, early 80s. But then they started falling away from specialized hardware. We talked about that actually a little bit in previous classes, or actually in the class that we missed last week about power consumption, and started using more stock commodity hardware. And so these specialized operating systems also kind of fell out of use. So we're not using specialized hardware anymore. We're probably not going to use specialized operating systems anymore either. Today, the most common path is to take an already existing operating system and just change it until it suits what you need it to do. So, if we take a look at the top 500, we can really kind of see a story about where operating systems lay in high-performance computing today. Any guesses as to which operating system dominates in high-performance computing? Probably already know. Linux, yeah. Oh, is it on the slide? Cool. Sweet, thanks. Any guesses as to how many Windows machines are on the top 500? One. There's one. Yeah. What about Macs? 0, yeah, absolutely none. Although Mac is Unix-like, so I don't know if it even qualifies as its own separate version or not. But yeah, so it's really Linux. Linux or Unix, which is, of course, the precursor to Linux. But why is that? Why the heck do they use Linux? It might be because they're a bunch of nerds like us who love Linux, or maybe you don't love Linux. I don't know. I don't want to speak for you. But there are actually other very good reasons as well. So Linux, as compared to other operating systems, It is very modular. I can swap the pieces in and out as I need to. It's very generic. That means it can run across many different forms of hardware. Although Windows, I think you could also argue, can run across many different forms of hardware as well, right? It's very scalable, and that's particularly important in the field of high-performance computing. Windows does not scale particularly well. Of course, it's open source, which makes a big difference because we can change it to make it work however we want, right? And you can't beat the cost either. It's usually free. Although in a lot of cases, you might actually purchase a version of Linux to get the support that comes with it. Potentially, it depends on what you want to do with it, right? And then in terms of architecture, any idea what kinds of architectures we're running on high performance computing? Have you taken a look at top 500? Taken a look at any of those statistics? I mean, it's a pretty good guess, pretty easy guess, actually. Most of them are going to be Intel x86 architectures, but there are others, right? So Intel, AMD. Intel, I think, is the dominant one. I think they have 80 to 85% of the top 500 nailed down on their architecture. But there are still a fair number of Spark architectures and PowerPC architectures on the list. And AMD does have its share as well. But perhaps, one of the biggest factors keeping Linux on high-performance machines is just the fact that it's been the operating system of choice for decades now. So if you wanted to switch to Windows at this point, all of the libraries you've been using, right, all of your entire code base would have to be reworked to work with that new operating system. And that's a lot of time. That's a lot of resources that you have to spend doing that. So Linux is definitely the king of high-performance computing. Absolutely. So let's talk about, if we want to change the operating system, if we want to tailor Linux to our own particular needs, then what are some of the kinds of things that we can do to get more performance out of it? We're not just going to download, the most recent image of Ubuntu and slap that on a supercomputer, right? I mean, I bet actually you probably could to some extent do that. But if you want to get the most performance out of it, like, we don't need a GUI for this stuff, right? We don't need a lot of the extra utilities, right? They come with a personal operating system. So, the kinds of things that we need to consider are what types of nodes exist within my architecture. So I've got compute nodes. I've got nodes that are dedicated to the file system for input and output, right? Or a lot of high-performance machines will have a client-server type of architecture where there's a server distributing, maybe it's instructions or other kinds of control information to a series of client nodes within the system. So my operating system needs to be able to take those different node types into account. We definitely care about communication, so I'm not going to rip the networking out of the operating system. That needs to stay, right? You need to be able to talk to one another. So the first idea I want to talk to you about, the first operating system, high-performance operating system that I want to talk to you about, is one that's going to take the operating system and segment it to match the different types of nodes that exist within a supercomputer, within a high-performance computer. And so it's going to be a distributed operating system, right? I'm going to have some nodes over here that have a particular piece of the operating system on it, and then another batch of nodes over here that are going to have a different segment of the operating system on it. So the way that this works from a high level utilizes microkernels. And these microkernels are sitting very, very close to the actual hardware, the actual chip itself. Their job is to manage memory, right? Manage processes and threads, input and output, and communication that occurs between processes. And that's about it. That's about all that it's needed to do. So the actual management of the system is kept separate from the operating system itself. So if I need a node to follow a certain set of policies, to become part of a certain partition of nodes or something like that. It's not the operating system's job. That's going to be a separate control system that's built off to the side of my high performance machine. But it's important to note that from the perspective of our users, we want all of this to feel like it's just built right in. So if I'm a programmer for one of these things, I don't want to have to go jump through a bunch of hoops, right, to get my code to work. I want to be able to have it work on anything, including the supercomputer. And so in terms of how we can actually distribute policies, right, how we can actually distribute information about what nodes are doing which particular task at any given time, we have a few options to consider. A centralized approach is going to be kind of like that client server that I talked to you about earlier, where I've got one sort of service node here that's going to distribute policies. It's going to tell each of these client nodes what they should be doing. You're an IO node, you're a compute node, right? You're something else. So that's one way of managing these particular policies. If we take a decentralized policy approach, then it's kind of like a tree structure where this node will tell its neighbors, and then in turn each of these will tell their neighbors, right? And then each of these will tell their neighbors until everybody's received the message of what they're supposed to do. And then finally, if we want to go fully distributed, then what that means is that it's basically a free-for-all, right? I inject the policies at a few different points throughout the system, and they just broadcast it out to whoever will listen, right? And eventually, it will make its way across the entire system itself. So that's kind of a high-level overview of how operating systems work in general across these systems. And now what I'd like to do is switch to our first of two operating systems that I want to talk to you about today, which is based on a very famous supercomputer, IBM Blue Gene L, to be more specific. There are many, many, many versions of Blue Gene computers. So you see the paper here. Like I said, it's kind of old, but this was such an important system, such an important landmark system in high-performance computing that people are still talking about it today. So Blue Gene L was first developed in 2004 for IBM. It was the fastest computer in the world for 3.5 years. So from 2004 to 2008, this Blue Gene L computer was the best computer in the entire world. I forget where it was actually stationed. I believe it might have been at Lawrence Livermore, but I'm not entirely sure about that. It probably says in the paper. Just to give you an idea, performance-wise, we were talking about 280 teraflops. What are we at now? Anybody remember? Petaflops. Yeah, we're up at petaflops now. So at least an order of magnitude higher than where this particular machine was, but that's still really fast. That's still a lot of power. This particular implementation that they talk about in the paper had 131,000 cores. Or 131,000 cores. They were dual core processors, so you split that number in half, and that will tell you the total number of chips that you had in this entire system. And it drew 1,400 kilowatts of power. So a pretty hefty system indeed. All right, let's talk about the design. So before we talk about the operating system, let's talk about the design of what they wanted to get out of the operating system. So sort of some high-level design decisions. Their primary concern, believe it or not, was budgeting. So they wanted to make it so that smaller development teams could write for this particular machine. They didn't have to put massive teams of programmers at work on these particular programs because paying people to write code costs money, and they wanted to save money. Yeah. In terms of developers, that's a good question. I honestly don't know. I've never personally worked on a computer system of this size myself, so I couldn't tell you. That's a good question, though. I do not know. But they were intending to shrink the size of the development teams to make writing code more cost effective. Of course, they wanted to learn from their predecessors and do better than they had in the past. And then they wanted it to be flexible. So they wanted it to be extendable. If I want to add more things onto it at a later point in time, they wanted that to be particularly easy. We'll show actually some experiments towards the end here that talk about how extendable it actually is. And they wanted it to be modifiable as well. So if a different kind of program came along or a different kind of job came along, they wanted the operating system to be able to adapt accordingly. Their main principle was that the structure of the operating system, the software, in this case refers to the operating system, should reflect the underlying structure of the hardware. And so before we can talk about the operating system, then we have to talk about the hardware. Here is the high-level view of the hardware of Blue Gene L. You see over here, this is where we're primarily focused. These are going to be our compute nodes. These are the nodes that are actually crunching the numbers, doing the computations. It also comes with a set of I/O nodes whose sole purpose in life is to manage file system access. So you see they're connected through an Ethernet network to the servers that contain the data, the stuff. So the idea is that these I/O nodes insulate these compute nodes from having to worry about any kind of latency due to the file system. That's sort of the goal here, right? And then we have this service node that's going to use one of these three systems to propagate policies. Because one thing you have to consider is that, if this node's a compute node for this particular job, it could very easily be an I/O node for the next particular job, right? They're configurable. They're all the same architecture, so they can be whatever they need to be. And then these front-end nodes are where the actual users interact with the system to submit jobs, right? Test their code, etc. Let's dive in a little bit and take a look at one of these nodes in particular, what actually is involved. You can see that over here are the actual cores. We've got two cores with double precision floating point units. You can see they're actually PowerPC chips. IBM was on the PowerPC bandwagon for quite a long time. In fact, I think they still kind of are on the PowerPC bandwagon. See, we've got an L2 cache. There's also an L1 cache you can see that's embedded on the single core, right? This L2 cache is actually shared across the two cores. And you can see that it uses a snooping system to maintain cache coherence across those particular cores. We'll actually talk a little bit about cache coherence in just a bit, right? And then they each have, what does this say on my machine here? 2 gigabytes of DRAM, I believe. No, that's not right. 2 megabytes of L3 DRAM that is shared. So L3 cache, essentially. Oh, here's the 4 megabytes of DRAM that I was looking for. So on-chip memory. And then, actually, perhaps more interesting is it's connected to 5 networks. So there are 5 different networks in this particular system. The Ethernet network over here is what connects it to the I/O system, to the file system, to get the data. This JTAG network is used for the policy distribution, so the control network. This Taurus network over here is used for computations, for spreading around data, for the actual computations that are taking place. And then these final 2 networks, the collective network is used within node partitions. So I actually split nodes up into particular partitions. We're going to take a look at that a little bit. So within the partition, we use the collective network. And then this global barrier network is used for, I believe it's also a control network. You see it's used for barriers or interrupts, right? So system level stuff. So that's kind of the architecture in a nutshell, right? So now that we've talked about the hardware architecture, we can move on and talk about goal for today, which is the operating system architecture. We're going to take these compute nodes and these I/O nodes and break them into partitions that we're going to call P sets. And each P set is going to contain one I/O node, so one node that's in charge of talking to the file system. And then however many compute nodes I decide are required for a particular job or a particular batch. So then these partitions, I'm sorry, I called the P sets partitions earlier. That was a mistake on my part. We've got P sets, which are actually encapsulated within a higher level of the hierarchy called a partition. And within these partitions, every P set has to contain the same number of nodes. So a partition can contain many P sets, but the configuration of each of those P sets must be identical. And then it's actually these partitions that are going to run a single task, which will then, that single task will be distributed across the various P sets. The P sets themselves are purely software implemented. There's no physical connections. There's no hardware connections for these P sets. So the idea behind the P sets is that they can be flexible. We can change them at any time. And create additional I/O nodes if we have a particularly an I/O heavy job, or fewer I/O nodes, and more computation nodes if we have a computation heavy job. And so speaking of jobs, it would be useful then to talk about the job model. What are we actually running across these nodes? Jobs are going to consist of course, many processes, and these processes are going to communicate with each other through message passing. So MPI that we talked about on Tuesday, that's what they're using here. Every process is going to have its own private address space. So the processes cannot talk to one another except through the messages. There's no shared memory going on here, right? And the processes related to a job are running only on the compute nodes. So the I/O nodes are not going to worry themselves with the processes at all. The I/O nodes are actually closer to the computers that we know and use on a regular basis. So the I/O nodes are going to run Linux. They're actually running a pretty close to standard version of Linux. They didn't say what distribution, although it's IBM, so I'm guessing some form of Red Hat, right? That's what they do. And on the I/O nodes, they actually only use one of the two cores that are available, which seems very curious, right? Why not take advantage of that? In the paper, they mentioned that on the I/O nodes in particular, they had cache coherency problems. And so the way that they got around that was to disable a core within these I/O nodes to alleviate those particular issues. So then, now that we have an idea of the architecture, now that we have an idea of how jobs execute on this particular system, we can start to talk about the actual operating system itself. For the compute nodes, they're going to run what's called the compute node kernel. And this kernel is going to do the bare bones of what's necessary to execute these processes. So the compute node kernel is in charge of things like creating the address space that's necessary for the processes, loading in the code and the data for the processes into memory. And then after it does those simple tasks, plus maybe one or two other simple tasks, it's going to say, all right, here you go. And the process is going to have full control of the node from then on out. So it's a very small code base. It only takes up 1 megabyte worth of memory, which is good for multiple reasons, right? It's not going to be heavy computationally. It's also not going to be heavy on the memory. It's not going to place an excessive load on memory either. So we want as many resources available for the actual computations as possible. It's not doing memory management for us. It's not doing scheduling for us. So there's actually no scheduling at all on these. What does that imply? Yeah, so the job itself is coming in through the control network. Exactly right. Yeah. And even still, we can extend this out. Right? How many threads are running on this? 1. I can't schedule anything. So there is exactly one thread that's running, and it's running all the time. I'm not going to preempt it. I'm not going to swap it out for another thread. I am devoting my entire set of resources to performing this one task, right? Not even the operating system is going to come in there and preempt it. The operating system is going to do its little setup, and then it's going to get out of the way. So we're devoting 100% of our resources to the process. We can't do that on these computers, right? It would be very, very difficult. I think perhaps impossible. Maybe with a bit of work, you could figure something out to actually run code on the processor without getting any kind of interference from the operating system or other programs that are executing on your machine, right? So they're really squeezing every ounce out of this hardware that they could possibly get. The only thing that the compute node kernel is going to do during process execution is handle system calls. So we still have to concern ourselves with system calls. We're going to talk about system calls actually right now. There are a few different cases. So if we have simple system calls, things like system time, telling you what time it is, then the kernel can just handle those directly. Those are easy. Those are quick. No need to worry about those. If we have I/O system calls, then we're going to ship those out to the I/O node, right? That's what the I/O node is for, is to handle I/O operations. So those are going to be transferred off the chip somewhere else. We're going to talk about what that looks like in a little bit. So if I need to access the file system, that's going to go elsewhere. If it's unsupported, then I'm just going to throw an error. I'm just going to say, sorry, I can't do that. Some examples of things that are unsupported. Anybody have any ideas of some system calls that we wouldn't be able to do? Kind of talked about on the last slide a little bit. I'm sorry? Forking, yeah. Because I've only got one thread, right? So I can't create any more threads. Forking is out. It's not supported, right? Can't do it. And there are some other unsupported system calls that are listed in the paper as well if you're curious about what it does and doesn't allow. In total, there are 68 Linux system calls that are implemented. Some of those are handled by the compute node. Some of those are shipped off to the I/O node, right? And then 18 that are specific to the compute node kernel itself, so that were added on as a modification to this particular operating system. So that's the compute node side of things. That's the compute node kernel. The other part of this operating system that we have to talk about is the I/O node. So the I/O node really has two main tasks in life. We need to distribute work and data. So actually, the I/O node plays a role in starting jobs. When I begin a job, it's actually going to be launched within a pset by the I/O node. The I/O node is going to be the one that waves the flag to tell everybody to begin. It's also going to distribute the data at the very beginning. So however that data is split up, that's going to be handled by the I/O node. And then during execution, if there's any requests for the file system, the I/O node is going to handle those requests. Remember, though, it's handling those requests not just for one compute node, but for an entire set of compute nodes, whatever compute nodes are included within that pset, right? So let's take a look then at what this operating system looks like. This is a more traditional form of Linux. It's embedded Linux. Have any of you taken, actually, Dr. Liu teaches some embedded programming classes here. Has anybody taken those? They're really cool, actually. I've taken one or two of them myself. It's a lot of fun. It's very, very different than what we're used to. So embedded Linux, as you can kind of imagine, is used more often in embedded devices like sensors, right? Things that are out in the field. Very low power. That's kind of a nice added benefit to this particular operating system. There's no swap space. What's the swap space? Yeah, so if you're a Windows guy, it would be equivalent to virtual memory, right? Yeah, that's basically the same thing. If I run out of memory, then I can load stuff off the disk. That's the swap space. So there is no swap space, though, not in this particular operating system. The root file system is all in memory. So if you go on a Linux system, right, and you go to root and you see user and bin and et cetera and all that fun stuff, that on this particular system, it's all going to be in memory. It's not going to be on disk at all. A lot of services are taken out. In fact, the two primary services that it includes, can anybody guess based on what we've been talking about? What are the two primary types of systems it's going to include? Daemons. I'm sorry? Network. Yes, that's one. So TCP/IP stack is going to be on here. That's what it uses for communication. What's the other thing it's going to do? What's it use the network for? A couple of different things. Right? Communicating with the compute nodes is one. It also uses the network to do what? It's an I/O node, so it's I/O. I'm sorry? The bus, I mean, there is a bus in these nodes, but we're only using one core, so we're not actually using the bus necessarily. It's going to talk to the file system, so it needs to know how to do file system operations, reads and writes, right? That's one of its main purposes in life. And so the main process that's running on the I/O node is going to be this control and I/O daemon. And it links our compute nodes to the rest of the stuff in the system, primarily the file system, right? Primarily the file system. But also including things like whatever's necessary to kick off a job that you can see up here on this particular slide. And so what happens then when one of these compute nodes decides that it needs something from a file? Here you can see a system call, scanf, right? Give me a piece of data from a file, please. What's going to happen? Well, it's going to make its way down to this compute node kernel. That's the operating system of a compute node within this system, right? And then that's going to get shipped out over this collectives network, one of those 5 that we saw on one of the earlier slides, and eventually make its way to the I/O node for that particular piece set. So eventually this system call makes its way to the I/O node, and that I/O node says, okay, I need to go figure out where that file is and figure out what it needs, right? What this particular compute node needs. So it sends off the read request over the network to the file server, right? Gets the data back, and then ships that back across this collective network to the application that needs it. So that system call actually has to make 2 hops, right? Actually more than that. It has to go out and then back just to get that data from the file system, which seems like it's probably a bit inefficient, and you wouldn't be wrong to say that, right? As opposed to if I was connected directly to the file system. And then what you have to do, what you have to consider that complicates this even more is that, you know, here I see 1 compute node and 1 I/O node. Well, for this 1 I/O node, there's probably going to be dozens of these compute nodes that it's handling these types of requests for. Not just 1, but many compute nodes that this I/O node is going to handle requests for. Excuse me. So how can we make this process more efficient? Right. That's something that we need to consider. That's something that we need to discuss a little bit. I think. Oh, I do have that somewhere. Hang on. Oh yeah. Okay. We'll get back to that in just a second. But you can see that this interaction does keep things simple on the nodes themselves. So I think you would hopefully agree with me that by shipping those system calls out, the compute node can go off and do other stuff while it waits for that system call to return with the data that it needs. It also keeps the footprint of the operating system, that compute node kernel, very, very light, very, very small, so that there's more resources available for it to do other things, such as the actual computations that we want the compute node to do. So it also keeping these things separate also improves the security. And by security, what I mean here is, you know, interference with other things that are running on the system. By sectioning things off into p-sets, I provided isolation between applications so that I don't have to worry about conflicts across multiple applications, multiple jobs that might be running on the system at a particular moment in time. And really, I'm going to show you some experiments that they performed in just a little bit. Keeping these separate improves scalability and the performance of the overall system. All right. Just a few small pieces yet until we talk about the experiments, actually. So if you remember from, I'm not going to go back to that original slide, but one of the other types of nodes that were available were these service nodes that were in charge of controlling the nodes, telling the nodes which version they are, whether they should be the I/O nodes versus the compute nodes. So how did this work? How do we actually tell a node to flip to be one or the other, right? Well, the way that this works is, you see one of its jobs down here is to load the operating system code. The way that that works is based on a set of personalities. So based on the personality of a particular node, that dictates whether I'm going to become an I/O node versus a compute node for a particular job. You can see some other things that the service node is used for up here. So by operation and monitoring, right? That's things like monitoring the power supply, monitoring the fan, energy consumption, things like that. But in terms of these personalities, so what information does a compute node need to be a compute node? And what information does an I/O node need to be an I/O node? Well, you'll see that there's a lot of things in common between these particular personalities. Things like how much memory we have. Things like my physical location. Where am I located in the overall scheme of the system? But there are also some different values that the compute node needs from the I/O node. So a compute node within a torus, do you remember what a torus was? We talked about that actually last Tuesday, was it? What do I mean by torus? Yeah, it's like if I imagine a grid of nodes computed together, and then I take one edge of the grid and wrap it around and connect it, and then I take the top and I do the same thing, right? That's going to be a torus. So I need to know my location within that torus. Where am I in relation to my neighbors? Not just where I am physically, but where am I in relation to my neighbors? What P set am I a part of? What's my rank within that P set? My MPI rank within that P set? The I/O node needs a little bit more. You see down here, we've got a lot of networking stuff. So what's my MAC and IP address? That's for the TCP IP stuff, the networking stuff, right? IP addresses. Where's the location of the file server, right? Tell me where the file server is. So the I/O node has a lot more networking information. The compute node has a lot more information related to data distribution, task distribution. All right, let's talk about some experiments. The last part of this paper laid out a few different experiments that they performed on IBM on this Blue Gene computer. Of course, they did many experiments on this machine. It was the fastest machine in the world. So I believe they used it to do environmental research and probably also some military research, since it was at Lawrence Livermore. They do a lot of military research there, I believe. So they did many experiments on it, but the ones that we're interested in this particular class are experiments related to the performance of the machine. So how well does this thing actually work? How well does the operating system actually work on this machine? Is this division of labor actually worth the effort it took to come up with the scheme and implement the scheme? So they tried a few different experiments. They tried one based on socket communication, right? So compare sockets, which is a pretty typical networking way of passing information from point A to point B, to what we're using in this class, which is message passing. So they wanted to know, right, what's the comparison between the two on this particular system? They wanted to test how good it was at file system access, because that was the whole point, right, was separating the two out so that the file system access would be efficient, more efficient, less of a bottleneck than it potentially could be. Then they did some work on multi-program, multiple program, multiple data applications. So what that means is within a job, I could actually have multiple sets of code running. Instead of all nodes running the same code, I could have a set of nodes running different code. within the same job. And then finally, they did some benchmarks on this particular machine. Of course, we know for a fact they did the Limpack benchmark, right? Because they were on the top 500 list. So socket communication, right? In relation to MPI, they just really wanted to know if it could be done. And not only that, but how did it compare? So can I do it? And how does it compare to the message passing implementation that's traditionally in use? In order to get this system usable with sockets, it required some modifications to both the compute node kernel and the I/O kernel, so the I/O daemon. So in particular, the compute node modifications involved adding the particular system calls that were necessary to implement sockets within the operating system, and then shipping these out to the I/O daemon, which then had to be able to handle those system calls as well. So how much did that overhead play into the performance? In terms of the I/O daemon, these socket calls can potentially block for an indefinite period of time. This is really, really bad because these I/O nodes are handling requests from many particular nodes, so they can't sit there waiting for one blocking call to return, right? They need to be able to handle the next request in the pipeline. So what they did is they actually used non-blocking calls, and the way that they did this is they took that blocking operation and they stuck it into a queue, and then they periodically polled the queue to see if the operation was finished. So the trick here was finding a balance between polling the existing processes and then handling incoming networking requests. This experiment is kind of an overall experiment to judge that division of labor between compute nodes and I/O nodes. If by passing things off to the I/O node, can it efficiently handle the many requests that are coming in from a compute node, right? That's kind of what they're testing here. And here is a plot that shows us some of the results. So what we're looking at is messages being sent via sockets here, not via MPI. And you can see that within the I/O node, right, the message that are within the sockets, the messages being sent and received both reach up close to the theoretical peak of 120 megabytes per second on this particular network, especially as we increase the message size, right? With smaller messages, latency is a factor in terms of overall bandwidth, right? But if I start sending larger messages, I start to reach that overall peak bandwidth of the system, which means that sockets actually are a viable form of communication on this system, thanks to that division of labor, right, between the compute node and the I/O node. So that was the first experiment that they did. The second experiment had to do with file systems. So the compute nodes themselves don't care what file system's in use. They're not dealing with the file system at all. They don't touch it, right? That's not their job. The I/O nodes are the ones that are in charge of talking to the file system. So they wanted to see how far they could take this. Nowadays, there are lots of different file systems in use. Back when this paper was written in the mid-2000s, the idea of a parallel file system was sort of a new concept. Not super new, but relatively recent concept. Nowadays, we have lots of parallel file systems. Have any of you guys worked with parallel file systems? Any of you worked with Hadoop? No? Oh, interesting. Well, we're going to talk about Hadoop later on in the course, probably a little bit. And we'll talk about parallel file systems at that point in time. But the nice thing about parallel file systems is I can take a bunch of data and distribute it across many different nodes. And it should theoretically increase my file system performance, because then instead of having to read everything off of a single disk and having that one disk be a bottleneck, I can now be potentially reading from many different nodes at a given time. So I basically increased the parallelism of my I/O operations by using a parallel file system, right? And so they wanted to know, can we optimize the performance of these parallel file systems? What's the bottleneck of using these parallel file systems? So they connected it to a specialized parallel file system, GPFS, which is the general parallel file system, which is still in use today, although not particularly common anymore. And this file system was hosted on 32 servers. So distributed means spread out across many different nodes, right? So I have 32 dual core servers hosting this file system, 8 disk controllers, 448 disks times 72 gigabytes per disk. I can't do that math in my head. It's a lot of space. A lot of space. And so how did it perform? You can see writing is always going to be slower than reading. That's just always going to be the case. You can see that's definitely the case here. The nice thing to pay attention to on this particular plot, so what we're looking at is megabytes per second reads versus write versus the number of compute nodes that are actually performing read and write operations. So you can see as I increase the number of compute nodes that are bombarding the file system, that it actually scales fairly well up into a point, right? And so you see there's a bend here where eventually it says, I can't handle any more write requests, I'm done. I'm saturated, I've hit my limit. And then the same thing for reads, but it lasts a little bit longer because reads are less intensive than writes on the particular file system. In the paper, the authors state the bottleneck within the, anybody have a guess as to what the bottleneck was? Why did it flatten out here and here? I'm sorry?
The queue? The size of the queue?
The queue length. I think you're on the right track. Where is the queue going to be for this particular? I guess it's kind of hard to make this judgment without knowing a little bit about the parallel file system structure to some extent, but you're getting close. It's something that was on this slide. It's the disk controllers. The disk controllers were being overloaded, which is where the actual queues for read and write requests are being stored for the file system. So you were pretty much right. Yeah. So the disk controllers are the ones that are taking in the read and write requests for the file system nodes themselves, and they got overloaded. It wasn't the file system itself that got overloaded. The nodes could have provided more output, input and output, but the controllers were unable to handle the requests that were being sent from the I/O nodes. So, I mean, the solution to that is just more disk controllers, right? Or better high-quality disk controllers, either way. The third experiment was that multiple program, multiple data experiment. And this one was actually very basic, very simple. When they first designed and implemented the system, it could only do single program, multiple data, which means that every node within a particular pset, within a particular partition, had to run the exact same code. But they were able to extend the operating system to include multiple program support. So now I could have multiple programs executing within the same partition. This was one of their design goals. They wanted to show that it was extendable. And so this experiment was that proof of concept. We can extend this operating system to suit our need. And then the last one, perhaps more interesting, is benchmarks. So they took a single node, a single compute node, and ran the NAS parallel benchmarks on it with two different operating systems. They did it with the compute node kernel, the specialized operating system that they designed for BlueJean, and then they did it versus a traditional stock Linux operating system. Right, so I've got my basic operating system on the same set of hardware, right? They both were on the same set of hardware. So any differences could be attributed primarily to the operating system, and you can see the results here. I have the compute node kernel on the left. Two measurements were taken: the overall time to execute the benchmark, and then the speed in terms of millions of operations per second. And so you can see these are various NAS parallel benchmarks. I remember what some of these stand for. IS is integer sorts. LView is lower upper decomposition of a matrix. Oh gosh. EP is for embarrassingly parallel. I forget what the other ones are for, honestly. But the more important takeaway here is to see how it compares to the Linux system here. So you can see the same measurements. Over here, we can see the percentage of time that Linux took for each one and the percentage of operations that Linux took versus the compute node kernel. So for integer sort, which is actually the best result on here, we see that Linux took 300% longer than the compute node kernel to perform the same benchmark. So it blew it away. What we can see for the rest of them is a much more modest but still noticeable improvement in terms of overall running time versus a traditional operating system. So overall, the compute node kernel was more efficient at running these particular benchmarks than a traditional operating system. And then they took this a step farther and did a few experiments regarding some additional benchmarks that we haven't talked about yet, but let's talk about them now. They did experiments using scaling. So what's weak scaling again? What do I mean when I say weak scaling? We definitely talked about this. Or if somebody wants to operate the opposite, strong scaling, I'd take either one. Anybody remember what the difference is? Yeah. Yeah, you're getting there. Yeah, you're heading in the right direction. Which one's which? Can you describe strong versus weak scaling?
Strong is from columns essentially
Mm-hmm. So you actually have it backwards. That's weak scaling. But yeah, you're on the right track. Weak scaling is I add more nodes and I also increase my problem size as I add more nodes. Strong scaling says I keep the problem size constant, but I just throw more nodes at it and I expect it to finish faster, right? So for strong scaling, what do I expect to see? If I have a plot of execution time with strong scaling, what do I expect to see that plot look like? Yeah. You hope it goes down. Yeah, you hope it decreases because I'm giving it more stuff to work with. I'm giving it more power. What about weak scaling? What do I expect weak scaling to look like? In terms of execution time. So this one, I'm increasing the problem size proportionally with the number of nodes. So what does that mean in terms of overall execution? Ideally. I mean, it should just be hopefully a flat line, right? No change in execution time whatsoever. Perhaps a small incline due to communication, depending on how communication heavy a particular program is. But if there's no communication concerns, then I would hope it'd just be flat, right? So let's take a look. They ran both of these experiments, weak scaling and strong scaling, and compare it to other supercomputers of the time. This plot is a little crazy to read, but I'll point out the interesting parts to you. Over here we see execution time on the y-axis, the total number of processes, so how parallel is this on the x-axis. And they actually had two Blue Gene computers, one interestingly named Watson, not the same Watson that you know probably, a precursor to that one certainly, but not the same one. And then another one called Big that was also running Blue Gene L. And that's going to be these guys right here. This is for the, this is for the weak scaling. So the one where the problem size grows proportionately, right? The other ones you can see are different supercomputers at the time, and all of them, as the parallelism increases, they start to spike up. Why do they spike up like that? What's the problem? Most likely? It's hard to say definitively, but we can at least guess, think about it a little bit. We see the flat that I was talking about, right? This is the good news. We see that it's flat, which is what we hope to see with weak scaling. So for Blue Gene, we see that is in fact the case. For these other ones, we see that they're not flat. They're flat for a little while, which is good. And then as we get more and more parallel, they start to spike. Where do those spikes come from? Communication, most likely. the more processes I have, the more communication I'm going to have. It's going to overload the system. That also speaks to the division of labor that's present in this operating system, right? I've taken a lot of the communication aspect of it out of the computation node kernel and put that burden on the IO node so that the compute node kernel can keep doing its thing without having to worry about the communication aspect. It mitigates those effects. Now, that being said, I think if you extended this graph out, eventually you would see these spike, right? It's not going to go out that way forever. I don't think. You would see it spike eventually. But we want to delay that spike as long as possible. That's weak scaling. In terms of strong scaling, what we see here, again, is the parallelism. And notice the number of processors, right? It's getting very large, up to 70,000. And that's only about half of what they had. No, I'm sorry. That is the full amount because they're dual-core processors. So they had about 70,000 dual cores on the machine. And then this is actually speed up. So we hope to see linear speed up as I add more processors, right? As I add more processors, the speed up should go up. The dashed line here is ideal speed up. And we can see that the actual speed up is very, very close to that ideal line. In fact, this data point, it shows it even higher than that ideal speed up line. That seems a little odd, right? We talked about that a little bit. There's a couple reasons why this could happen. Some of it is, variance, measurement bias, something like that is certainly possible. In fact, probably the most likely case here, I would imagine. But the fact that it's very close to that ideal speed up is a very promising result for this particular experiment. Cool. So to wrap it up for our first operating system, they showed that designing an operating system that follows the design of the architecture can work and can be effective. In fact, more effective than a traditional operating system. Separating this out has some pretty desirable qualities. Makes it more scalable, both weakly and strongly, right? Improves performance, provides that separation of that division of labor, right? And so IBM is still using this to this day. They're not using the exact same operating system, or it's been through some iterations since then, assuredly, right? But they're still using this division of labor concept, and other people have also hopped on that bandwagon since they were encouraged by the results that they saw here with Blue Gene. Any questions about this? All right. Yeah, question.
So I didn't talk about this later, but I guess I don't understand why those two videos are something that's
All right. Let's the socket one. Yeah.
So I guess, but in order to prove that it was like a reasonable strategy, you have to compare it to some of the information or something. These are just like some of the.
Sure. So they have MPI implemented on these machines, right? That's kind of what they were contrasting. What they wanted to prove was that a socket implementation was usable, that it was a viable option. And the way that they did that was they knew the max bandwidth of their network was about 125 megabytes per second. And they just wanted to show that they could approach that 125 megabyte limit, which you can see on the plot that they clearly got pretty close. That's all they were trying to show. Yeah. Good question. Any other questions about this stuff? You should definitely go back and read the paper. There are some things that I kind of glossed over, some things that I left out due to time. It's a great read. It's a fascinating paper. So check it out if you have some time. If there aren't any questions, let's take a little break. Let's take a bathroom break. Be back here 5-10 minutes, and we'll talk about our second operating system.
until you get the class.
That's what I'm transfer didn't work.
Yeah, this is. It's totally wrong. Yeah, I know.
Yeah.
That was the thing, like, So my theory is that we're not getting any units off these people because it's such a small population.
Yeah, we created.
Yeah, we'll throw no. Get some positives to that. Right? I think this will always be nice after you pass 16.
Yeah, we're
I know in high school they had this, they didn't want to install it first because they felt like every person would it's like schools like that. Rather than having should just go.
Yeah.
And I found people that have less muscle memory.
Yeah.
So you're
Let's do it back this road. Yeah.
I did it my first step. I think you're
I can ask.
Yes. But that works. The biggest thing, yeah, is to get it.
No.
Do all some of the process.
Right. So the problem that I know they're gonna come, I know they're gonna
Be
say,
scared.
I'm gonna ask them, they're gonna say, we use machines. Let's calm down.
Okay.
And that's usually like right before school starts.
Okay.
So, almost positive that's what they're gonna say. I'm gonna ask them anyway, I don't know what they say.
Sure.
next week. Sometime. I do know, they have math. So it's similar to math.
On the.
Not on the Linux side, but
Yeah.
on the
Yeah.
Linux side of things, they
Yeah.
do. And your home folder is high. Right, so
Yeah.
that might be.
So here's part of the problem.
Well, yeah, I actually, it'll, I think I'll be on there.
This might be.
Oh, yeah, stuff.
Seems
Yeah.
like it'd be nice, like, I could wrap it into like shelves. Run it.
So if you could.
Yeah.
Well, this is, you know, we've done.
Yeah,
That's not.
so you're hoping to get it installed on the Linux, on the Linux side.
So I might want to.
on the Linux side thing. That's actually probably easier.
I'll ask. I'll ask and see what they say. I can't make any promises, but
Okay.
it doesn't hurt to ask. Yeah.
Averages out to 30, I'm sure, when you average your 62.
Alrighty, let's continue. Actually, while I was on break, I remembered a couple of announcements that I had forgotten to tell you at the beginning of class. The first one was regarding the previous homework assignment 2. I'm hoping to get those graded by tomorrow, so I know you're probably wondering when I was going to get those back to you. Tomorrow is hopefully when I'm planning on grading those assignments. And then the other thing that I wanted to tell you, on Tuesday, when we talked about the cluster, I ran into some troubles with the cluster, you remember? Especially when it came to executing code across multiple boxes on the cluster. I figured out how to fix that problem. I needed to, if you're curious about it, what happened was the version of OpenMPI that the IT department put on the cluster was using a particular networking library, a particular open source networking library that was just not playing well with our network. And so what I had to do was, after some Google searching, I figured out how to disable that particular networking library and switch it to another one. It was just a flag to the MPI exec calls. So I uploaded a new version of the zip file for homework 3. I sent out an email about this. Hopefully you already grabbed it. It has those flags in there. You can actually look at the scripts and see what those flags are that I added. And so if you use those flags with MPI exec calls, you'll probably get better results, especially on the cluster. On the cluster the other day, you remember it wasn't working at all if I was using more than one physical box, right? Now it will actually work as intended across multiple boxes. So it should all be above board now. Yeah, so those are the only announcements that those were the announcements that I was trying to remember earlier that I forgot. Okay, any questions about that stuff before we continue on to part 2? Okay, so part 2, this is going to be something a little bit different than what we just talked about. So the previous operating system was is now especially a well-established operating system. It was interesting at the time. It was novel at the time. Has now become, you know, a pretty accepted way of doing things. This next operating system that I want to talk to you about, this next high-performance operating system, is still kind of in its infancy. It's a few years old, but hasn't gained a whole lot of widespread acceptance yet. So it's kind of still finding its way a little bit. Still has some kinks to work out. It's called Barrelfish. Has anybody heard of Barrelfish before? No? Okay, cool, good. Let me fill you in. So the premise of Barrelfish is that with the rise of multi-core processors, the operating systems then should have adapted, and they didn't. That's kind of the whole premise of this operating system, is that we have multi-core processors now. We should have operating systems that are capable, or perhaps more capable, of taking advantage of those multi-core architectures. So their solution, you know, is to get away from this operating system design that has worked for, you know, the last 20, 30 years for single core systems and was just made to work on multi-core systems, and redesign a new operating system from scratch that was intended to work on multi-core operating systems, right? So they implement what they call a multi-kernel operating system that matches this distributed nature of hardware these days. It's designed to be general purpose, so they're not trying to fill any kind of particular niche. They're just trying to make an operating system that performs well across many core architecture. So why are they doing this? We kind of already talked about this. You know, our systems are becoming more and more diverse. So what I mean by that is we have more and more different types of cores on our systems. Nowadays, it's not uncommon to, you know, of course, take advantage of the CPU, but also try to take advantage of the GPU within a particular machine, right? And GPU computing in general is becoming very popular within the high-performance computing community, as we're going to discuss in a week or two. So, you know, we have some cores that are using particular instruction sets. CPUs are mostly Intel, right, these days. But then we also have this other instruction set that's gaining traction, GPU instruction sets that are gaining traction. And there is no one operating system that really can take advantage of both of those particular diverse sets of cores. The operating systems that we have are really sort of generalized to handle the most common case, which is going to be your typical consumer grade machines, right? We want something that's adaptable, that can take advantage of any kind of distributed system that it comes across and perform well. And so one big premise that they lay out at the very beginning of the paper is that this interconnect matters. And what they mean by that is that communication between cores is becoming more and more like message passing. So what does communication between cores look like now? If it's not message passing, then what is it? We talked about this a little bit, or a lot actually.
Cache coherence.
Cache coherence, right? The cores that we use now, the multi-core architectures we use now, are shared memory. They're using cache coherence to talk to one another. those messages that we send along the bus, you can kind of see how you might draw some parallels between those and message passing. And so the idea behind this operating system is, well, then why not just go for it and implement everything using message passing and ditch cache coherence. So that's what they're going to try to do. In order to illustrate this point, they tried to prove that messages cost less than shared memory. And so what we see here is a chart that shows us number of cores on a particular shared memory chip, right, versus latency to write a particular number of cache lines. The symbols on this are pretty hard to read. Whoever designed this plot should be fired, but I'll try and walk you through it because it does paint an interesting picture. So if you look at the non-filled in black shapes, so like the triangles, the squares, the X's, and the pluses down here, these are shared memory systems that are altering various numbers of cache lines. So we see SHM1 is changing 1 cache line. SHM2 is changing 2 cache lines, 4 cache lines, 8 cache lines, etc. And what you see is changing 1 cache line down here, the latency is relatively constant, right? That's good. As we start changing more cache lines at the same time, we see the performance starts to increase rather dramatically. And by the time we get up to 8 cache lines, the difference between changing 1 and 8 is pretty drastic, right? What they're trying to show then, to contrast that, is message passing. So the black filled in triangles then are the same idea. I'm going to change some lines within cache, but this time I'm going to use message passing to do it. And the way they set it up is they use a centralized server to manage the message passing queues, and they send messages between various cores, right, within the system to manage the same thing that a cache coherency protocol would. And so you see here that the difference between doing this with 1 cache line versus 8 cache lines, well, it does get worse the more cores I add because, of course, I'm going to have to send more messages, right? That's not completely unexpected. The difference between 1 and 8 cache lines is almost negligible, right? Very little difference, much better than the gap between the two. And then you can, between the shared memory ones, and then you can also see that the server that's used to oversee this message passing process is pretty constant in terms of performance, right? So they're trying to show that message passing could be a more efficient way of doing things.
What do you mean by a cache line? Is that like 1 word or page?
A cache line is usually multiple words. It depends on the cache implementation, but it's pretty common for a cache line to represent up to 4 words, even 8-word cache lines, I think, exists in the world. But yeah, it's usually measured in words.
So it's not a whole page?
I don't want to say that there isn't a cache that could do a whole page, but I don't think that that's typically the intended idea. It's possible that somebody out there somewhere is doing stuff like that, but usually it's a small number of words. Okay. So, some of the conclusions that they are drawing from this, right, is that cache coherence is not going to fix the problems of these multi-core architectures. They call it a Band-Aid. They say that it's not a permanent fix. It's not a permanent solution to scalability within multi-core architectures. That's one thing that really hurts us, actually. When we talk about scalability within multi-core architectures, the cache coherence protocol is what's dragging us down. The more cores I try to cram onto a chip, the more the cache coherency protocol gets in the way of performance of those cores. And the protocols, it's not helping things that those cache coherency protocols are getting more and more and more complex as time goes on. They're not getting simpler. So messages, on the other hand, are getting easier to send. Shared memory actually, uses messages as part of their cache coherence protocols. They send messages across the bus, right, to different cores. That's part of how it works. And then other cores snoop the bus to read those messages. So it's kind of a message passing system already. Operating systems can also take advantages of messages. They're driven by events. They're driven by interrupts, right? They're driven by other system calls, things of that nature that happen over the course of program executions. GUIs are also driven by events, right? I click on something that fires an event. I can use messages to handle those events. Is sort of the conclusion that they're drawing from this. And so what do they want to do to try and push us in this direction of using messages as opposed to cache coherence? They propose 3 design principles of this operating system. They want all inter-core communication to be explicit. That means if I want to open up the hood and see the messages that are being passed in order to keep cache lines consistent with one another, I can. Can you do that right now? If I want to see the messages that are going down the bus for cache coherency, could you do that? Has anybody ever tried? I have. I'm not going to say it's impossible, but it's definitely not intuitive in terms of how to do it. I was not successful, right? Cache coherency is built into the hardware. It's built into the chip. So it's very difficult to see what it's actually doing down there. We can talk about it from a theoretical standpoint. It's difficult to actually see what's actually happening. So they want to make all that communication explicit. They want to bring it out into the open. They want to make this operating system hardware neutral. They want this operating system to be able to operate no matter what kind of hardware you've got running beneath the surface. No matter the architecture, no matter how many cores you have, they want this operating system to work and to perform well. And then the other thing that they do is they view the state of the operating system as replicated, not shared. And what that means is, we're going to talk about this in more detail, but what that means is if I make a change to the operating system, perhaps I queue something up for the scheduler, right? I fire off a new program that needs to be scheduled. I'm going to change the state of the operating system locally on myself, on my own personal core. And eventually, some point later on in the future, I'll notify the other cores so that they also have that particular piece of information. They know that I've scheduled a program. But I'm not going to wait until all of the other cores get that information to move on, right? We'll talk about that more in detail in just a little bit. So what they designed is a distributed system that uses messages and no shared memory whatsoever, which is kind of a lie. We'll talk about that in a little bit. So in terms of explicit communication, here's what they did. Right? I already kind of explained the problem of cache coherency in that it obscures what's actually happening. We can't really see it so well. We can't see what's happening underneath the hood. If I have explicit communication, it behaves more like a network. The messages you can think of as similar to packets flying around on a network. And I can actually use then network optimization techniques to help me optimize the path that a message might take through the operating system, for example. I can start pipelining these things. I can start batching these things together in this particular case to try and optimize performance. We're going to use non-blocking messages here. So the core can go off and do something else, right, while it's waiting for a message to be sent or received. And in general, it just makes analysis easier, right? I can see what's happening. I don't have to talk about it from a theoretical standpoint. I can see what's actually happening and use it to diagnose problems. To try and make things hardware neutral, their operating system only has 2 hardware-specific things that it took into account. One is the actual messaging mechanisms themselves, how our messages pass from point A to point B. That does require some knowledge of the hardware, right? I have to know where it's going, where it's coming from, which is going to be hardware. And then the interface to the hardware itself, basically the drivers that are needed to power the hardware and make it work, right? Those are the only 2 things that are going to be hardware specific in this particular operating system. Everything else is going to be generalized to not rely on a particular set of hardware. And so now we can actually optimize message passing independent of the hardware itself. Whereas with cache coherence, right, since that's baked right into the chip, the optimization of cache coherence depends entirely on the architecture. since it basically is a part of the architecture of the hardware, right? And then finally, replicated state. Let's talk about that one, right? The state of the operating system under the current scheme has to be accessed by multiple processors. So there's one scheduler, right? The operating system has one scheduler that handles the scheduling of all the cores on your chip. And all of the cores need to be able to access that scheduler to submit tasks to be scheduled, et cetera, et cetera. Under the current system, it's locked so that only one core can access it at a time, right? It has to be. Otherwise, we have race conditions and all kinds of other nasty things that could occur. In this case, what they're saying is not that the state has to be replicated necessarily, though it could be. It could be replicated across the multiple cores, as in each core now has its own copy of the scheduling queue, for example. They're not saying that that necessarily has to happen, but what they are saying is that they're going to treat that scheduling queue as if it is, in fact, replicated, even if it's not. So I'm just going to write to it and worry about whether I have consistency problems later, right? And try and fix them after the fact, rather than lock. So no locking at all. I'm just going to do what I need to do and get the heck out of the way, right? So I don't have to block. I don't have to wait. Consistency then, how are we going to maintain consistency? Let's say we actually do replicate the scheduler across all of the cores within a system, right? And then I have two cores that each schedule, or maybe all four cores in a quad core system, schedule a job to the scheduler. They submit a job to the queue, but they each have their own local copy. How am I gonna maintain consistency across those four copies? What's the mechanism I'm gonna use? Oh, come on, guys. What's the mechanism that this operating system is using to communicate between cores? Message passing. I'm going to pass messages, right? We use message passing for everything. Let's just hop on the message passing bandwagon. Yeah. So that's what they mean by replicated state. All right. In order to actually apply this model, they had some challenges. So if I have a shared cache, a shared L2 cache, right, or even a shared L3 cache for that matter, since you could have a shared L3 cache, what the heck do we do with it? Because I'm drifting away from shared memory into the case of distributed memory, right? So I don't really want to worry about this shared memory architecture anymore. I'm trying to get away from cache coherence, right? So what the heck do I do with this? Some other considerations that they had to take into account is this consistency, keeping all these copies consistent with one another. That's not free. Sending those messages to make sure the scheduler queue is consistent across all cores, that's not a free operation. Although locks aren't a free operation either, right? But we do want to make sure that it can perform well. With messages, we have to take latency into account. So latency being what in this case? What do I mean by latency? Yeah, so I send a message, right? How long does it take from when I start to send that message for it to actually get to where it's going? And then there's also, unfortunately, an increased burden on the programmers, developers of this system to control consistency across applications that are running on this particular system. So these are some of the issues. In fact, they've written papers on some of these issues to address them individually that you can find on the internet, on the website that I believe I linked to on the course webpage. They have addressed some of those issues, but as of the time of writing this paper, those were some of the open issues that they were still considering. So then their real goal at the time of writing this particular paper, they've written several papers since this paper was written. This is kind of the introduction to the system. At the time of this writing, their primary goal was to get performance that was comparable to a modern operating system. They weren't even trying to be better. They were just trying to be as good as, right, similar to modern operating systems without using cache coherence, using message passing instead. That was all they were trying to do. It's a pretty modest goal. They were trying to demonstrate scalability, that we can throw a whole bunch of nodes at this particular system and it'd be able to handle it without massive degradation in performance. They wanted to show that using message passing would allow optimization to take place, right? Or optimization, not just in the message passing, but also optimizations that could take advantage of particular topologies. So by topology in this case, we're not talking about nodes within a network per se. We're talking about cores, right? Cores being cores on a CPU and a GPU and maybe some other systems that you have hooked up to the same system, right? So how can we exploit those topologies for the best performance? Can I offload some work to the GPU and have it compute those certain chunk of data and bring it back? So they did run some tests. They did implement this message passing scheme. We'll talk about how in just a little bit. And then they ran some tests on it to see how well it performed. And they actually used 4 different test platforms. It was important for them to show that this operating system was adaptable to many different kinds of systems. So they wanted to use many different kinds of systems to perform these tests. You can see the systems that they listed here from Intel, one Intel system, so 2 4-core Intel systems, 2 dual-core AMD systems, 4 quad-core dual AMD systems, and 8 quad-core AMD cores, right? With varying amounts of cache. Some even including shared cache, right? Shared memory.
Just get rid of L1 cache.
Gets rid of L1 cache. I mean, ideally that core would be able to take that cache for its own private use at this point. Cache coherency is out the door, but we still have message passing that we can use to keep things consistent across multiple cores, right? So we can still use the L1 cache. In fact, I think it would be dangerous to get rid of L1 cache since it's so valuable, it's so fast. Yeah, it's the shared ones that become a little bit tricky because how do we chunk that up across the different cores? It's kind of application specific to some extent. What is this core working on? What is this core working on? Is there going to be contention? Are the cores going to start fighting over that shared memory that's available? They actually came up with some clever uses for that shared memory that I'll show you in just a little bit. So what does this operating system actually look like when they deploy it? You see down here we have the metal, the hardware, right? They can't turn cache coherence off. It's on the chip. So that's kind of frustrating. The cache coherence is still there. They can't turn it off. Can't do anything about it. But they can circumvent the process. They can pay attention to their messages, right? To some extent. Then we see the CPU drivers. That's going to be the most hardware-specific part of this operating system, right? The code that's going to drive the chip itself that sits on top of it, directly on top of the chip. Here's our user space, and you can see the user space consists of a series of monitors that are talking to themselves via remote procedure calls. Those are going to be the form that messages take in this particular operating system. And then the applications run on top of that user space. We'll talk about what these monitors represent in just a little bit. First, let's talk about the driver. What do those drivers look like? What's their purpose in life? They're closest to the hardware, closest to the metal. So you can see they're in charge of time slicing, accessing the hardware, driving the hardware. These do not interact with other cores at all. They're just basically in charge of the chip that they're sitting on top of. So single-threaded, can't be preempted. They're just doing their one task, which is driving the hardware. That allows it to be very small. 7,000 lines is relatively small for a kernel, right? Plus some assembly code. So like I said, this is the most hardware-specific piece of the operating system, and also, I think, the least interesting piece, and that's coming from a hardware guy. What's a little bit more interesting are these monitors. So these monitors now replace what we think of as a traditional kernel in this particular operating system. They're designed to operate on a single core, which seems a little odd, but it makes sense when you think about it. I want a distributed operating system, so I'm going to deploy an application that's specifically designed to control each individual core, and then those applications are going to have to coordinate with one another, right? That's the distributed part. Instead of having one operating system that's in charge of managing all of the cores. That's not really distributed at all, right? So we're spreading the workload out to these monitors that are sitting on these single cores. These replicated data structures, I keep using the scheduler queue as an example because it's the one that's stuck in my head right now. There are others, are kept consistent by an agreement protocol implemented by sending messages. And so these monitors are basically in charge of any communication that needs to happen between processes across various cores. That's their main purpose in life. And so then how do processes work under this scheme, especially multi-core processes, right? Well, a process is represented under this operating system by a collection of dispatchers. So if I want a process to run across many cores, I'm going to have one dispatcher on every core that I want that process to execute on. And that dispatcher will be sort of in charge of executing that process on that particular core. And then using the monitor to help communicate between the other cores as necessary to get the job finished. These dispatchers are scheduled by that CPU driver, just like the monitor is too, actually. It's scheduled by the CPU driver. So any user level threads are scheduled through here. In fact, they managed to implement POSIX threads under this particular scheme without any problems. All right. Let's talk about this communication. That's perhaps another very interesting part of this scheme. What do these messages look like? How does this communication actually work? That's sort of a big deal in a message passing based operating system. So you see, all of these communications occur with message passing. All of them are explicit. We can see all messages that are being put in place. But there are different ways of passing messages for different purposes. The one purpose I want to focus on is cache coherent memory. So we don't have the cache coherency protocol anymore. Well, we do, but we don't want to rely on it. We don't want to rely on that cache coherency protocol. But we can, interestingly enough, use shared memory as a channel to pass messages to keep memory consistent with one another. So what that's going to do, we're going to use these cache line size messages to talk for one core to talk to another. This is only for point to point, so one to one core talking to another core. So what this looks like, how this works, is the sender of a message is going to start writing stuff to cache sequentially, and the receiver is going to pull the last word of a cache line. Why the last word? Any idea why it would pull the last word?
Like the size of the message.
Yeah, the size of the message is one cache line, right? So I want to make sure to pull the last word because I want to wait for the entire message to be finished before I pull in the entire cache line, right? So I don't want to look at the front of the cache line. That would only perhaps get me the start of the message. I want to wait for the last word of that cache line to be written and then pull in the entire cache line. That's going to be my message in this particular case. Right, so as soon as it sees that last word has been written to, it's going to pull in that line. And then the message has been passed using the shared memory that's on the chip. So they're taking advantage of that shared memory to implement this message passing system, which I think is pretty clever. They're using a shared memory architecture to implement a distributed operating system. This is all abstracted out behind an interface. So from a programming perspective, we don't have to worry about this polling mechanism, this cache line mechanism. We just have to make the appropriate function calls. It's also transport independent, so I don't necessarily have to worry about whether this is going over a network or across the bus or anything like that. It's capable of handling all of those situations. The potential downside here in terms of performance is polling. Right? If I'm expecting a message, I'm going to sit there and poll the last word of that cache line. So how can I do that efficiently without wasting a whole bunch of cycles waiting for that message to come through? Well, they actually talk about that a bit in the paper. We'll see some experiments based on that in just a little bit. In terms of memory management, this is something else that we need to discuss. We talked about, you know, the what to do with the different cache levels and the shared L3, L2, L3 caches, etc. And physical memory itself, right? RAM is still a global resource that has to be shared across all of the cores. There's no way around that. There's no such thing as a distributed RAM. Although I actually suppose you probably could do that. Now that I think about it. That makes me curious. I'm going to Google that later and see what's out there. But anyway, back to the task at hand. Barrelfish uses a capability system to manage memory. And so what that means is that if an application requires a certain amount of memory, it will try to change the capability of memory, basically acquire it for its own purposes. And that includes RAM, but also page tables, also other things related to memory as well, look-aside buffers, things like that. And then the CPU driver will make sure that the processes are all agreeing with one another, that no two processes try to acquire the capabilities of the same chunk of RAM, for example, that they're actually acquiring memory that exists on the machine, for example, and things of that nature. Let's see. We're almost to the experiments piece of this. So in terms of these shared address spaces, right? They don't necessarily want to get rid of shared memory entirely. There's still a lot of applications that rely on this shared memory process. So what they do is they coordinate these dispatchers in order to make advantage of shared memory resources. And the way that they coordinate it is by sharing a virtual address space and the capabilities that we just talked about. Capabilities can be shared across multiple cores if necessary, and also managing threads. These can all be shared across many cores via the dispatchers. And then, of course, to keep everything consistent, we're going to use message passing, just like we use for everything else. And so then finally, the last neat little feature that they implemented, and then we'll talk about some experiments, is this knowledge and policy engine. So they call it a system knowledge base. I think the name of this has actually changed since this particular paper was published. But it manages knowledge about the hardware, including information about what kinds of communication protocols are available, right? What kinds of buses are available, what kinds of networking is available, interconnects, what kinds of topologies exist. So where are the nodes in relation to one another and how are those nodes connected to one another, right? All of that is kept in this knowledge engine, and then it uses this to optimize the system. So if I need to get a message from point A to point B, what's the fastest way to do that? It's an interesting question because I could be sending things across a bus. I could be sending things across a network. Right? I could be sending things from a CPU core to a CPU core, or I could be sending things from a CPU core to a GPU core, or a GPU core to a GPU core. And depending on who's doing the sending and what kinds of connections take place, that's going to dictate the overall speed of these messages. And so this knowledge base is continually tracking the messages that flow through the system and updating its knowledge accordingly to provide the best performance available when it comes to transferring messages. Okay, are there any questions right now before we take a look at some experiments? This is always, to me, the experiments are always the most fun part of any paper. So to figure out how well this worked, they tried a few different experiments. One involving TLB shootdown, one involving just overall messaging performance. So how good are these messages being sent? One involving computation. So heavy computation workloads. It's nice if the messages work really well, but can we actually do some heavy duty computations on this thing? And then also they wanted to take a look at IO performance as well. So let's take a look at some data. Let's take a look at some numbers and see how well this thing does. First, let's talk about TLB shootdown. Oh gosh, I always forget what the T. I always forget what the T stands for. It's a look-aside buffer. I would just skip the T because I always forget what it's for. But TLB shootdown. So what this is doing, right? The TLB maps virtual memory to physical memory. So a process access is virtual memory, but all those virtual memory locations are mapped to physical memory. That's what the TLB does. TLB shoot down is the process that takes place when one process acquires a set of memory. It then needs to notify all other processes that, hey, you know, I've acquired this from my own personal memory space. You can no longer use it. Flush it out of your virtual memory space. You can no longer use this particular chunk of memory, right? So processors use TLB shoot down to acquire chunks of memory, restrict access to private memory, right, from other processes. This operation was chosen because it's relatively simple in terms of the operating system, but still requires coordination across all of the cores that exist within a system. So they have to maintain this consistency by sending messages to invalidate TLB records when pages are acquired, or actually sending out messages when pages are released as well to say that, hey, you can use this memory location again, right? Linux and Windows do this using interrupts. So the way that it works is the way that it's going to work here. So Linux and Windows use system interrupts, which means it's going to interrupt the process and say, hey, update your buffer to do this, right? The way it's going to work here is we're going to write the operation to a common location and then notify every core to go read that particular value, read that location and get it. The information using, I'm sorry, what I just described is actually the interrupts. I apologize. The interrupts work by writing things to a particular location, interrupting the cores and saying, go read the information at this location to update your buffer. The barrelfish way of doing it, of course, is going to use messages. We're going to rely on the monitors. So the monitors are going to send a message out to other monitors that say, hey, get rid of this mapping that you have, if you have it. And it will wait for acknowledgments as well. So it's a message out and a message back. This is going to be higher latency in general, but they're partially testing how well their knowledge base works here to gain performance. So they tried 4 various approaches. They tried a broadcast approach. Might help if I actually sketch these out. So a broadcast approach is, you know, I'm going to say, here's the monitor that's acquiring the mapping, right? It's going to send it out to all nodes, every single node at the same time, just broadcast it out for the whole world to see. A unicast approach is going to say, send it out to a node, right, one at a time, and then send the next message out to another node, and then send the next message out, one message at a time, instead of broadcasting it out for everybody to see at once. Multicast is going to kind of chain it. So I'll send the message here, which is going to then send the message here, which will then send the message here, right? And then finally, NUMA aware. NUMA, does anybody know what NUMA stands for? NUMA stands for Non-Uniform Memory Architecture. And what that means is, imagine, the simplest case I think to imagine is a 4-core system, right? I have a chip with 4 cores. And let's say that the message is originating here, right? Is it going to take as long? Is it going to take the same amount of time to send this message to all 3 of these other cores? What do you think? Are all of these messages going to take the same amount of time to reach the other 3 cores if I send them here? No, why not? It's a very almost deceptively simple explanation for why the answer to that is no.
Physical location.
The distance. It's literally just, this one is a little bit farther away than this one and this one. Now, if you take this very simple 4-core example and expand it out to like a whole bunch more cores, it becomes even more clear, right? The distances between cores are not equal. So it's going to take longer for messages to reach some cores than others. So with that in mind, what's the most efficient way of sending messages? Which message should I send first with that information in mind if I want to finish the fastest amount of time? First way, yeah, I'm going to send the message out to the furthest core first, and then the closer cores. works. That'll give you the best time. So it's kind of multicast, but with a twist almost, right? Where I send things out to, imagine I have 2 of these, right? Or however many of these that I want. We're talking massively parallel systems here. I'll deliver the message to this core and this core, and then these 2 cores will be in charge of sending out to the furthest one, and then the closest ones within their individual chip. So it's kind of like multicast, but it also takes distance into account. Cool. So how do these different schemes work? How well do they perform? We can see here the number of cores being varied, right? Versus the latency and how long it takes these messages to get delivered. And the broadcast, which is the first one where it just sends it out to all of them at the same time, you can see as the number of cores goes up, it scales, which is actually a bad thing in this case. We don't want it. We want flat latency, ideally. That's what we're looking for, right? So broadcast performance is not the greatest. Unicast is not much better, which unicast is individual sending. Why is unicast better than broadcasting it? Any ideas? Because it knows where it's going. Yeah, I mean, that's part of it, right? It knows exactly where it's sending this particular information to. I'm sorry. Sure, overall traffic on the network is going to be reduced because I'm not sending out a broadcast to all cores. I'm sending out one message at a time. Yeah, exactly. Multicast, that's the one that kind of does the chain reaction thing. You can see that it's pretty level, but it increases kind of in steps. And if you look closely, it's roughly every 4 cores. So that means basically as I add more chips, more physical chips on, I see it take a little jump, which kind of makes sense, right? Those chips are going to be farther away than individual cores within a single chip. And then the best one that you can see is this pneumo-aware multicast, which gives us that relatively flat latency that we were looking for in this particular example. So those were promising results. It showed that message passing could be used to accomplish this particular operation with a relatively reasonable latency using pneumo-aware method. So they took this a step farther and compared this then to existing operating systems. Again, they wanted comparable performance to existing operating systems. So you can see Windows is this guy here, right? Linux is the boxes here. Oh, hey, Linux is better than Windows. We already knew that, right? I'm sorry, my bias is showing. Barrelfish is here. So you'll notice that for small numbers of cores, Barrelfish is actually worse than both, right? But for increasingly larger numbers of cores, Barrelfish starts to outperform the others due to its relatively flat trajectory compared to the existing operating systems. So that's a positive result, right? That's a pretty positive result. All right, let's talk about messaging performance. In particular, let's talk about polling. What was polling again? What do I mean by when I say polling? Yeah, I'm polling that last word in the cache line, right, to see if the message has arrived, to see if the message is finished being written. So they tried to model the performance of this message passing under this particular scheme. How wasteful is it to poll like this? So they generated this very simplistic model. The terms that you see here, P is the amount of time spent polling. So how many times am I sitting there just asking, are you done, are you done, are you done? C is the amount of time spent sleeping, right? So eventually I'm going to stop polling. I'm going to go to sleep and wait, and then wake up and then start polling, right? Give the message time to get there. So they tried to develop some models to illustrate, the overhead and latency of these messages as it relates to the amount of time spent polling, the amount of time that was spent asleep. Actually, I had to start with latency, right? With latency, if the time that it takes, I'm sorry, T here is the arrival time of the message. So when the message gets to its destination, right? So the latency here If t is less than the amount of time that I spend polling, the latency is 0 because I'm sitting there waiting for it, right? It's ready right away. Otherwise, if I go to sleep, then my latency is going to be however long I was sleeping, because I'm basically, the message gets there, but I don't know that it gets there until I wake up, right? So that's kind of a latency that I'm eating as a part of that process. I guess I sort of skipped part of this explanation. I'm going to start polling, right? Poll, and then I'm going to go to sleep, and then eventually I'll wake up and start polling again, and then I'll go to sleep. Right? That's kind of what's happening here. So if the message arrives while I'm polling, that gives me the best latency. Otherwise, I'll get it when I wake up from my sleeping period. In terms of overhead, right? So again, t is the arrival time of the message. So the overall overhead, how long does it take for the message to get from point A to point B? If it arrives while I'm polling, the overall overhead for that message is going to be t, right? If it doesn't, it's going to be the amount of time that I spent polling plus the amount of time that I went to sleep, because hopefully it'll be there when I wake up. These are models that they use, and then they actually tweak these parameters. How long should I poll, and how long should I go to sleep in order to get the best performance using these particular models under their particular implementation. And in the paper, they state that P and C should actually be kept pretty close to equal. In fact, they found that if they kept P and C at around roughly 6,000 cycles, so I poll for 6,000 cycles, I sleep for 6,000 cycles. I wake up and I poll for 6,000 more, and then I go to sleep. That led them to the best performance. And then the next experiment, these are compute-bound workloads. So these are actually, again, the NAS benchmarks that we talked about with the Blue Gene, and we talked about earlier as well, right? You can see they're implemented with OpenMP. So they had OpenMP to work, because they did manage to get POSIX threads implemented in this particular operating system as well. And all that they're trying to show here is that with a few very small exceptions that you can see in this example and this example, all they were trying to show here is not necessarily that one is better than the other at these particular benchmarks, but that they were comparable. So a lot of these you can see they're almost identical, right? To Linux, all these are compared against a Linux implementation. Barrelfish performs comparably to Linux for 3 of the 5, and even for the remaining 2, it's not that bad. With the possible exception of this one, which is pretty horrible. If I'm reading it right, it's hard to see. Actually, this might be Barrelfish on the bottom there. It's really hard to see from this particular angle. Oh, okay, yeah, so it did better. That's good then. Yep. This one, it did worse. Integer sort seems to have done worse. And then finally, the last experiment that they did was I/O workloads. And so to test this, what they did was they actually developed a web server. So they wrote a web server application and ran it on a Barrelfish operating system. So that includes everything: the server, the NIC, system services, all distributed across separate cores. And then they compared how many requests per second it could handle, the max requests per second it could handle on the particular implementations. For Barrelfish, they had 18,000 and change requests per second, and on the same hardware for Linux, it was only about 9 requests per second that it was capable of handling. Okay? In fact, they were so pleased with this result that if you go to the Barrelfish website, which I linked to on the course webpage, the web server that they're using for their website is running on this operating system. That's pretty neat. So, to kind of start wrapping things up here, I think that they kind of reached their goal, which is to say, not necessarily to say that it's better or worse than any particular operating system, but that it's comparable. Since then, like I mentioned, they've written a lot more papers to improve this operating system and explain it in even more detail. If you go to the website, they have a very long list of publications that are pretty interesting to read. In fact, you can even download the source and try it out yourself if you feel so inclined. You could probably even do it on a virtual machine if you really wanted to. But this is still kind of a baby operating system. It's been around, I think, since 2009, 2010. So 4 or 5 years now. They're still working on it, right? There's still more stuff to come. But from this initial paper, this paper was published roughly when it first was introduced back in 2009, 2010. These results were very promising. And since then, they've managed to implement this on various architectures. You see Intel, ARM. This actually, Intel SEC Knights Ferry, I believe that's called Intel Mike now. They changed the name to Mike, which is, oh gosh, I used to know what that stood for. Something chip. Shoot. Anyway, Intel Mike is an interesting project performed by Intel where they put lots of cores on a chip. They're talking about many cores. So 32 cores, 64 cores, 128 cores on a single chip. That's what they're talking about with the Mike architecture, which seems particularly well suited to a distributed operating system such as this one. And then Beehive, which is actually a clustering system. Beehive is a system that's used to create clusters that I thought was pretty interesting as well as some other implementations that you can see on their website. And so throughout this process, you'll notice that I never really talked about this being run on a supercomputer. Right? In fact, the implementations they had were pretty modest. I think they had 32 cores, which is still, a decent amount, more than we have, right, on our machines, but not a supercomputer by any means, more like a small cluster than anything else. And so the stated design here is, very general purpose. But there's a little tidbit of information that I haven't let you in on. One of the big backers of this program is Microsoft. And so there's a lot of speculation in the community that maybe this is Microsoft's plan to get back into the high-performance computing realm at some point. Now, I first gave this talk, I think, 2 to 3 years ago, and we're still waiting for Microsoft to jump back into HPC. In fact, they're losing ground. When I first talked about Barrelfish, Microsoft, I think, had 3 computers on the top 500 instead of just 1, right? So we're still kind of waiting to see what happens. But Microsoft is behind this. A lot of people think that this could be something that Microsoft is going to try to push into high-performance computing, into supercomputing in the future. It's not quite ready for prime time yet, though. But it's an interesting question. Is this going to be designed for high-performance computing? We'll see. What do you guys think about this idea? Do you like it? Do you think it's a good idea? Think it shows some promise, or think they're barking up the wrong tree?
Scale really well.
It did seem to scale pretty well, and that was one of their stated design goals, right?
Seems to be the most important thing since individual core length.
Right. Yeah, I mean, we're dealing with more and more cores. In fact, if you go look at the top 500, they're not using quad-core chips. They're using 8-core chips at a minimum, I think, and more likely to use 16-core chips. Right? So massively multi-core stuff is coming. Will it ever hit our computers? I don't know, actually. Maybe someday. But it's kind of getting to the point, too, where, like, do you need 16 cores to check Facebook and Gmail?
Yeah, you must game install multi-core.
Right. I mean, for games, the GPU is the
Right.
primary.
One of like your games like Arma 3 or something actually uses multi-core or multi-thread. You can have to go.
Yeah.
It's very rare to find.
Yeah. I mean, yeah.
I feel like it's interesting that like the target audience for this might would be consumers. I guess with the idea that if you're pushing the computer never gets that support.
Sure.
So it's like the people who are actually going to be paying attention to this, right? People who set up data centers or people who set up everyone's
Mm-hmm.
kind of a, I don't know how big that but
There definitely is money. Yeah, there certainly is money. I think it's kind of a gamble. I think you're exactly right. They're not. They state that this is for general purpose, but I mean, come on. Like a lot of the machines that they ran this on were more cores than I would consider ever sticking into a laptop, at least today. 10, 15 years from now, I don't know what's going to happen, but I think their intentions of general purpose are a bit misleading or misguided at best. I agree with you. Yeah. It'll be interesting to see what happens. It could fizzle out and die away. And, if I teach this class next year or 2 years from now, I might have to swap this lecture out for something else. Who knows? But I think it's an interesting project. And I've even toyed around with the operating system itself. I haven't gotten too deep down into it, but I mean, it's pretty easy to use. They've made it pretty easy to use from a user perspective, which is a good thing, right? I mean, I don't want it to be super clunky. I want to be able to get on there and compile code and execute it, right? Just boom, done.
So you said that the cache coherency logic is still on chip, still in work. Does that mean that the locks that it implements are accurate too?
So I'm actually a little unclear as to how exactly they get around that cache coherency protocol. It's a good question. Clearly, they are doing something that allows them to ignore it to some extent, but it is on hardware. And to my knowledge, you can't go in and turn it off. Although I could be wrong about that. Maybe they did find a way to go in there and turn it off, or maybe they found some specialized chip, perhaps, that has more control over cache coherence protocols than what we have. Of course, I would never consider turning it off on my machine anyway. That would be catastrophic. But it's a good question. I would say take a look at some of the publications they have on the website. I bet they talk about that somewhere. Yeah, it's a good question. Any other questions or comments? Yeah.
You said you downloaded this fish.
I think the source is available. In fact, it's just a Git repo on their website.
So you said you used it.
Yeah, you can try it out. Why not? It's
Like, do you know, does it feel like,
so this was a few years back. When I ran it, it was pretty much all command line. I think there may have been a GUI at the time, but I was struggling to get it set up and executing. So I was pretty much just doing command line stuff with it at that point. And I'll be honest, it's been a couple years since I took a look at it, and it's still in active development. So I would be interested to go back and see how it's changed since then. In fact, I can pull up their website. We can take a look and see. It'd be a good way to end the class. Let's take a look at their website and see what information we can find out about it. Here you go, Barrelfish. So here's their Git repo, right? They just had a new release on June 18th. That was less than a month ago. So they're still actively working on this. They have a download page. Oh yeah, this is a lot more documentation than they had when I tried it out. Let me tell you, I would have killed to have some cool documentation like this. Practical guide, that sounds promising. Compilation, installation, hello world program. Doesn't have a GUI, that's kind of the thing, right? There's a simple program that you can run. Server side. I don't see like any screenshots or anything like that being offered. Seems a little unclear to me. There's the people working on it. Here's that list of publications that I was talking about. That would be worth taking a peek at. Although they haven't done much recently. October 2014 is the last one. Yeah. I don't see, let's see. Let's take a look at the fact here. Yeah, they're unclear about the GUI. Like I said, I wasn't messing around with the GUI when I played around with it a while back. That doesn't mean there isn't one. That just means I don't remember using a GUI with it. So best thing to do would be to download it and set it up and see what happens, I think. Mackerel. Oh, they named everything after fish. Go figure. Mackerel. What is mackerel? Command line. Yeah, it's a command line tool, it looks like. Yep. So all these are command line tools, which to me implies that it's still very much command line oriented. Hake is also the name of a fish, right? So Hake is a namespace utility, it looks like, for memory management. Oh, Hake is how they build barrelfish. Okay. It's a build tool. Yeah, it's all command line based stuff. Yeah. But yeah, I know, again, it's a little too late, but this would have been an awesome project idea. And I guess maybe not quite too late. I don't know. There's only 3 weeks left. I'd hesitate to say switch your projects now. But if you really, really are interested and you've got the time to devote to it, make a pitch to me. I'd be happy to hear it. Any other questions or comments I can answer right now? Okay, cool. If not, have a good weekend. I will see you guys next week. Remember, your homework assignment's due next Thursday, right? And I have extended office hours next week that I sent out in an email to make up for the lack of office hours this week. I'll stick around for another few minutes, too, if you have questions on homework assignment stuff. See you guys next week. Have a good weekend.
Yeah,